Okay, so welcome to Trusted Teachers, another video being the support that we needed. It's a computing video today, and one of the previous videos that we did was on integers, whole numbers. So today what I want to do is look at real numbers. So we've only really looked at how computers store whole positive numbers. These are known as integers. Don't do integers, old man. They are negative and positive whole numbers. But in the real world, we have to deal with decimal numbers, 20.75, 102.487, etc. And these are known as real numbers. And in computing, computer science, we use a system called floating point representation. It's a really simple system. And this is the decimal number 20.75. And in floating point representation, we have 0.2075 times 10 to the power 2, which makes perfect sense mathematically, because 10 to the power 2 is 100. 100 times this number here will take us back to 20.75. So the equals holds true. They are the same value, just written down differently. In computer science, floating point representation always starts with a 0 and then all the digits of the number. So this is a standard way of representing real numbers in a computer. The decimal point is always moved to be immediately in front of the best of the number. So 323.75, the decimal number is moved. In this case, it has been moved 1, 2, 3 places, so it's in front of all the other digits, and that becomes 0.32375. The power we have to multiply by to get our it's the same as the number of spaces that we move the decimal point. So we're moving the decimal point to the left here, 1, 2, 3 spaces, the power becomes 3. So 323.75 is equal to 0.32375 times 10 to the power 3. We move the decimal point 3 spaces. If we move the decimal point to the left, this power is always positive. With very small numbers, i.e. 0.00056, we have to move the decimal point to the right to get it in front of the rest of the actual number part of it. So that becomes 0.56 times 10 to the minus 3. Because we moved the decimal point to the right, the power is negative. We moved it 3 spaces, it's negative 3. Okay, and there's a number of decimal numbers here, showing you what they'd be like in floating point representation. So 23.67 becomes 0.2367 times 10 to the power 2, because we moved the decimal place 2 spaces. This number here, quite a large number, excuse me, 5,326.15, and then it becomes 2, 3, 4. 0.536215 times 10 to the power 4. We moved that decimal point 4 spaces to the left. Some small numbers here, 0.0025. That becomes 0.25 times 10 to the minus 2, because we moved the decimal point to the right. Having explained all of that, actually what we really need to know at this stage are these two terms, the mantissa and the exponent. The mantissa refers to this part of the number, the magnitude of the number, the actual digits, and the exponent refers to the power. Now, examiners get quite funny about this. It is just the power that it's raised to. The exponent is the 2, the 3, the 4, the minus 2 here, the minus 4 here, and the minus 3 here, not the base, which is base 10. Okay, so the mantissa is this number here, and the exponent is the power over here. And that's really all we need to be able to explain is how computers store real numbers. We don't actually have to do much in the way of putting decimal numbers into floating point representation, but we do need to know that this part here is the mantissa and the power is the exponent. Just for completeness sake, I've shown you how it would actually happen with a real computer system, because as we know, computer systems can only store binary numbers. So we have a binary number here, 1001.01. which is 9.25 in the real world. And we've got the Mantissa. We've moved the decimal point 1, 2, 3, 4 spaces to the left, and it gives us this, the Mantissa, all the other digits, times 10 to the power 4. But that 4 is a bit pesky because computers can only store binary numbers. So we have to take the exponent and translate that into binary as well. So ultimately our number 1001.01 is equal to 0.100101 times 2, because we're now in base 2 binary. And this number here isn't 100, it is 4 in binary. And ultimately what a computer stores in its memory is the Mantissa here and the exponent here. And that's all it has to store. It doesn't have to store the base, because in computer systems, the base is always 2, it's always binary. So that's the terms Mantissa and exponent, where they come from, explained. And for our purposes at this level of computer science, we need to know that this part of the number here is the Mantissa, and this part of the power over here is the exponent. That's been another Trusted Teachers video, being the support that we needed. Hopefully that explains real numbers, and thanks very much for watching.